Awesome. Greetings, healthcare colleagues. My name is Kevin Kawchak. I'm the founder CEO of ChemicalQDevice. This is discussion number 74, March 16th, 2023. So what you see in the screen is this is the composer view for KissKit. So if you haven't been on here, I'll familiarize it a little bit. So this folder icon is really important. It opens, so these are all available files to open on the left-hand side here. And this composer jobs is important too. And in specific, it's this little link, it view all jobs. So when you get done with your current job and after it's running, you can go do that. So that's basically those. So going back to composer, getting this here. And you'll see the circuit here. So the importance of this is quantum circuits are used in hybrid networks in literature to some pretty good results, up to 5% boost in classification accuracy. So this includes binary classification. This specific one is the binary classification for Alzheimer's disease. There's another network, probably one of the newer papers, it's a quaternary brain tumor as well. So what you see here is a collection of gates. I'll go through gates a little bit later. On the right side is the code. So this is very helpful. So I'll be touching on that as well. So I'm going to go ahead and get started. So what we see here is a 4-qubit circuit. Now the qubits are off by a number. They start at 0. So it goes Q0, 1, 2, and 3. And what I'm going to do is you can go to View and in Panels and then get rid of the code. And then you can see the measurements there too. So I'll try to stay zoomed in as much as I can. So basically, it's a collection of these initial states, Hadamard gates, and RYs. So I'm going to make this deeper. So deeper means left to right. So I'm going to add this RY. And then you can see it takes 4 of them. So 2. And then I can condense the code a little bit more here. And another RY. So there's advantages of deeper neural nets, and it's very specific to if you're running a quantum simulator or not. So I'm going to start adding some CNOT gates. So we started with 6 layers. So 1, 2, 3, 4, 5, 6. I'm going to build 7, and then 8. So I'm going to go +2, and I'll tell you why a little bit later. So you can see this one has a periodicity, and it's not a linear line like that. So this is essentially +1 layer. And then I'll show you another one here too. So adding an RY, which stands for, it's a polyrotational Y gate. And then I'm going to continue this pattern and with this 4th one here too. Now, the last set is, this is CNOT gates. And I'll show you the code with a lot of these. So this is CNOT. So if we count the layers up, so 1, 2, 3, 4, 5, 6, 7, 8. And this is perfectly fine. So if I were to check the code, I could go ahead and run this. And I've run this circuit, but I'm going to run a circuit that I haven't run before. Now, it gets a little trickier to add qubits. So the key to that is it's not inherently obvious, is you have to click on the Q3 or the latest one at +1. And +2. Now, the reason why I'm adding +2 is because of the CNOT pattern, you can't just add just a single qubit. And at that same time, C4 has to go up to 6, okay? So Q0 through Q5 is 6 qubits. C6 is 6 classical bits, and then I'll fix the end of the rest of the circuit a little bit later. So to do that, I'm gonna go ahead and add these. And yes, I mean, order can matter how you add things. This should be fine. So, if you go up, down, or left, right, those types of things. So I'm going to add this RY, this RY, and then I'll show you what happens with these. It's kind of intelligent. So I'm going to continue this pattern. So there's 1 CNOT, there's 2 CNOT. And then same thing with the RY. So for every additional piece of the layer, you're adding 2 CNOTs and 2 RYs. And it varies by circuit, but you have to figure out the pattern in your head. So you see how these look? So there's a space here, a space here. So similarly, over here, C naught, and then this C naught, and then you have this RY and this RY. So that's 2 out of 8. So I started with, it starts with 6. I built it up to 8 going deep. And now I'm doing all of this, building down. This is called making it wider, circuit wider, keeping the pattern and making it wider. And then after I build this up and do a little bit of code, then I'm going to run, and then so you can see what's going on. So, checking everything looks good. So there's a space, there's a space, there's a space. It's just how the circuit is. This is a 2023 published algorithm right here. The 4-qubit 6-layer one is. And you see, keep the periodicity, and then also, do this. And as practice makes perfect. So it won't let you run a circuit that, doesn't really, doesn't make sense. So you keep, learning from literature, and then, running new experiments. So you could see after this, there'll be 2 more. So basically here, and then on here. Okay, and it's really quite fun. It's somewhat of a game. The physics behind it, if you don't know a lot of physics, I was just on this physics discussion last night, is that it's challenging for sure. But what we're talking about is turns of a qubit is these, software gates is what they're doing. And we're almost done with this particular one before you get to the barrier, and after that, the measurements. So in specific, let's see, we don't need that. RY. And everything's looking good. And then for this last one, we don't have to do RYs after it. It just looks like that. So the circuit has been pretty much been built. Now to do the next part, it's been hard for me to do it graphically. So I'm going to go to view, and then and I'm sure there's probably an easier code editor. So then I can zoom in again. So then I'm looking for the code. So at the bottom, so let's see if we could zoom in one more time there. So you should be able to see in the lower right-hand corner where it says 106 barrier. So I had issues before running this circuit because the measurements would go into the gates. So I'm going to Q0, and you see it starts there, and then it's kind of quick to the trigger. So it goes up to Q3. So that was for the original circuit. So what I'm going to do is go Q, and then you have to be careful because you have to remember it's 1 behind. So if I'm at 6 qubits, it's going to end at 5, right? So there's Q4, and then here's my Q, and then this is going to be 5. Okay. So what it did is it ends in a semicolon. So you can see here. So this barrier now extends all the way from Q0 to Q5, which is 6 qubits. And then I'll show you again. So the measurements goes from qubit 0 to classical bit 0. And remember, the original circuit was 4. And I've had issues with these. These don't drag and drop very well. So what I'm going to do here is I'm going to copy one of these. So I'm in the bottom right-hand corner. And I'm going to go to Q4. Qubit 4 goes to classical bit 4. And then I'm going to go to Q5 goes to classical bit 5. Okay. So this should be good, and it's not showing any errors. So what I just did with code, which is what I found is easier, is I extended the barrier by 2 qubits, and then this classical, and it's best to learn from examples with that. So then I'm going to panels, so code editor, and then it doesn't show that either. So this is the full circuit. So 6 qubits, and then it's now 8 layers deep. I haven't ever run this one, so I'm titling this is the author's name is Shawar Kamati et al. 2023, and it's modifying +2 deep and then +2 wide. So the wide is attributed to the qubits. So this looks good. And then I'm going to set up and run this. And here's the quantum computer. It's this IBM Nairobi, 7 qubits. And that's all of my circuits that I've run on, has been Nairobi. So it doesn't seem to, okay. So I'm going to run, and then it's automatically in the queue. So I'll show you right now, just real quick, where this just went. So if I go to recent files, and then this particular one, and I can see more details. So it's going to show me this particular circuit that was just formed, and you'll see the queue. So it just says in queue, and you can go back to jobs, and these are all the jobs, and queue position is 8, which is really good. I've had it say up to a month to run, but it takes a couple hours, and it's always like an exaggerated kind of thing. So a queue position of 8, in there is pretty good. This should be, hopefully this should be done by the end of this discussion here. So I'm going to switch over to lab. So it occasionally does that. You just have to click the server. Now this runs Python code in a Jupyter notebook, and I like it pretty well. There's modifications you have to do to either the code or, these initial parameters, or setting up, the code to run between your Jupyter notebook outside of Qiskit. But this stores everything in IBM's cloud, which is nice. So my Jupyter notebook that I do my penny lane stuff is local. So they both have benefits. So again, I'm seeing this, so I'm going to tuck that back in with the file, and we're gonna, so this should be fully full screen. Now, what I'm showing here is basically, I just want to make sure everybody can see this. So I say live demo from quantum gates to healthcare algorithm design. And I went through piece by piece. So quantum circuit, quantum register, classical register, those are, qubits and classical bits, transpiling, what all these different things mean. I searched all over the web to find these. Some of these are common. Basic error, you'll hear a lot. It's a collection of quantum simulators. So this one is, unitary simulator is what I'm going to run off of. Matplotlib to display, and then these are basic things. If you've never coded before, you have to know something as these types of things, NumPy, math. Now here we go. So this is a typical notebook here. So I say this cell consists of 3 lines of code below. So there's the 3 lines of code. Now we can tell it's code because if you look at my cursor, everything in that cell has to remain either code or markdown or raw. So most of it is code or markdown. This stuff up before is markdown. It's not looked at as code. So I'm going to run this from top to bottom. So this is based on this Qiskit documentation. I highly suggest to go through, and what this is going to do is it sets up in order to analyze. So when I push Control Enter, the 1 shows up, meaning I just ran that cell. And then the next one is I'm going to click that cell. It could be anywhere. Control Enter, and then it just says I just ran that number 2, and this sets up the simulator. Now, quantum register, there's a couple different ways with quantum circuit and quantum register. Quantum register is the number of qubits that is going to follow. So when I hit Control Enter with there, it says 3. That's the 3rd line. Now keep in mind, I can Control Enter again, and it's running it again, but it didn't really do anything because it's already in the system. So the first gate I'll show you is unitary gate, and that's recognized by this .u. And then also in this one, it's a very versatile gate, and it also utilizes pi. So earlier on, I installed pi into this code. So this is what the unitary gate looks like for that specific one. Now to do the calculation is it shoots out these numbers, and you can compare these to IBM's. And then here's the P gate. So this again is a single gate. And what recognizes it different is this QC.P, okay? And then so you see pi over 2 comma Q, and then QC.draw is what draws it. So there's the P gate and then the pi over 2. And I think you could change the output of the, how these gates look like. So the P gate calculation, and there's an infinite number of gates. It's just, you just go by a certain number of them just so things don't get out of hand. It's just turning a qubit. So if you have, like a half turn, it's look at my thumb, and then now look at the fingers. And then a quarter turn is like that. And there's 8 turns, and I'll show you a little bit too. So we got the P gate calculation. Now the ID gate people don't use too much. It returns the same output as the input, but its thing is QC.I. We're using QC. It's ID and then in parentheses Q. The parentheses can change, right? Because before there's, you have to add certain things for certain gates. So there will come a time that you won't be able to use, graphical composer like I was just using, and you'll be copying, pasting, say repetition, like deep learning amounts of code for quantum. Here's the calculation, and then here's the X gate. Now the X gate is basically the NOT gate or the bit flip gate. It's one of the 3 Pauli gates, so that's the .X for that particular one. So keep in mind, these are all Qiskit oriented, and there's the calculation. And here's the Y gate. Now the Y gate is the bit and phase flip gate. It's the second 2 of 3 Pauli gates we'll look at. There's the output. And then here's calculation. And then here's the Z gate. You don't use as much. Phase flip. So the Y did 2 different things, and then the Z gate does this one. And then here's the calculation. And then this is very popular is the Hadamard gate. It sets things into superpositioning. It's considered one of the 3 Clifford gates. So in specific, here's the calculation, and here's the S gate. So it's square root of Z phase. Do you want to look at these like they're mathematical, manipulations and going from one to another, or you can. And then here's the S double dagger, SDG. So it's the conjugate of the square root of Z phase. So it's just, to not make it so confusing, you're just looking at it, it's just, manipulations to a single qubit. And then as we hopefully take a look at that code, here's the T gate. So it's QC.T, and then it drew it. Here's the calculation. Now, if I were to skip one of these cells, they're not that important because it's not like a register, like a quantum register. If you forget to update your register, you're doing 2 qubits, but it's still set to 1, you'll get an error. Now, here's TDG, so it's the conjugate of the square root of S, and then you have the RX. So again, I'm just doing control enter, control enter, control enter. So these are all the single qubit gates. Now here's the RY. So as you can see, still a single qubit. I haven't changed the quantum register, okay? And this is 4 out of 5 of the C3 gates. And then here's the calculation. And then here's RZ, which is the 5th of the C3 gates, rotation around Z gate. So they call it Pauli rotation or rotation Pauli Z gate. So we're switching over to 2 qubits. So this is really important. If you forget to update this, and same thing with other things with code and any code, this is important because it's, again, it just said 33. And if I were to run it again, it would say 34, right? But it has to be in there if your corresponding code, and it's not like other computer programs where things are just laid out. It has the memory, and you knew that you pushed the, to execute, and now it's in there. So this is the first 2 qubit. So the Q17 doesn't really matter. It's based on the previous runs. It's the 0 and the 1. So this is 2 qubits. So Q0, Q1, this is the C0 gate. And you can change this, and I'll show you in later runs from Q1 to Q0, and then the little dot is down here, and then the big plus is up there. And then again, calculation, and then here's the control Y. So if you want to be an avid coder, eventually you have to memorize all the gate abbreviations. Now I think they're different for penny lane and say for circ as well. So here's the calculation. Here's a control Z, so that's a dot CZ, and then run that, and then you see what that looks like. And then here's that calculation. And it's just repetition. If anything, if you want to get good at coding, just you find efficient ways. If you're doing deep layers, instead of dragging all these gates in the KISS kit, the composer is you can find out the repetition, and what a CRZ is, controlled rotation Z gate is. So it does take a fair amount of time to visualize all this. So we're getting down towards the triple gates to Foley and the Fredkin. So here's the CP, controlled phase. So some, I would assume you have certain ones that you're just comfortable using, and there's different ways to get to a similar solution, because when you're turning a qubit, you basically can go 360 degrees. But these are the ones that IBM Qiskit supports, in abbreviations. So here's the swap gate. You'll see the swap a lot. So it's qc.swap. And then again, you could flip the 1 and a 0. I'm not sure what it'll do in that. It'll still swap it. And calculation. Now here we're at three qubits. So this is the important part. This cell matters. So control enter. And then now it knows that it's only going to accept circuits that are meant for 3 qubits. So the Foley gate .ccx, and you'll see a 0, 1, and 2. I can't put a 3 in there because it doesn't, it's only set up for 0, 1, and 2. So that's the Toffoli gate. And here's that calculation. So Fredkin. So I hear other programmers talk about Fredkin. So here's the Fredkin. It's a 3 qubit gate. And here, so this is a little setup for other things. So those were all the single, double, and triple gates. So again, if I forgot I just ran, it does say 56, but I'll show you again. It'll turn to 57, control enter, and now it's 57. If you don't trust that number. So measurement is qc.measure, and this is what was in that previous circuit that we submitted to Q. And as you can see, this is setting up a different code, but it's basically saying 100% of the time the classical register returns to 0, and the output, it says that 0 to 1024. And here's another measurement, and then let's see, the output. This one is actually supposed to be closer to 50-50, and this is a quantum simulator, so this is kind of interesting. So half of 1024, there's 1,024 shots in between these two numbers. So if you were to take 524 then 500, that would get you 1024. So you see the split between that, and then here's the reset qubit. So this for mid-circuit resets. And keep in mind, some of these I even pass, there's certain conditions of using certain gates. So this has to be in that specific state. And then here's another one. So reset qubit calculation. It's showing correctly 0 out of 1024 gates. Other, like penny lane uses 1,000 shots, and it might make more sense. It just depends. You could change all these things, depending on how many experiments you want to do. So here's basically a reset gate 0, 1024. And then in this specific one, it's the conditional operation. So there's other things you can do. And this specific one is a qc.x, and then you have your q0.cif. So again, this is kind of like that deepness that's in there. And they say for this one, the classical bit shows up as 1, and then all the other quantum bits shows up as 1024, which is unique because usually you wouldn't have 1025 out of 1024, but it's just saying that you could do certain things with classically that you would traditionally do quantum. And then here you go. So here's another circuit. So there's this, the mid-circuit measurement, you'll hear a lot. And then this C.if conditional measure and draw. And for this one, it says get counts. So it's a similar type of thing. You know, the classical bit is accounting for the 1 with the 1024 shots. So here, this is arbitrary initialization. So I just ran it twice. And this is the output for it. And then in specific, we're gonna, so these are the calculations for that. And then the fidelity is 1.0. Well, I ran it before and it was 1 point several zeros and then a 4 at the end. So it's interesting that how this runs at different times. And here's basically, this is an experiment that I'm doing here. So I'm setting the register to 6 qubits. So it should be 0, 1, 2, 3, 4, 5. So you see up to 5. And it's a single to Foley, which is a CCX across 0, 1, 2. So that's one I experimented with. And then here's another one is, again, I don't have to update the register. The register stays the same. It's just the circuit has to match what I previously did. And then on this one, I instead of 0, 1, 2, I set 3, 4, 5 for this one. And then for the next one, okay, so here, I'm setting the register to 15, okay? So it'll go Q0, and then I did a bunch of Foley's. So 0, 1, 2, and this is where you learn, right? Is you just experimenting. Like this code, I just copy and paste and, you know, you just change the numbers. But to Foley, say this last one, 12, 13, 14. And then here's 12, 13, 14. Keep in mind that 74 we're not quite looking at. And this is adding on to that. And now you could start to see with the circuit, sometimes the zoom, but you can kind of get that idea. Okay, so quantum circuits are not going to remain small. You know, as hardware, even simulators get bigger, you're going to get deeper circuits, meaning left to right are going to get longer. You're going to get wider circuits. So this is 15 qubits. So you can see that. And then the next one is basically, I'm flipping the C0 gates. So instead of dot to plus, you'll see they go plus to dot. And it's just, you know, in that code, instead of this first one being 0, 1, now it's 1 to 0. And then on this specific one, it's, okay, I'm going to add a bunch of single qubit gates. So it's UPI, XYZ, H, S, T, so on and so forth. And again, it ends in 14, but it's really 15 because it's n-1. Now on this one, adding an additional layer, and this is just building it up more. And you can see it's printing pretty fast. This isn't the world's fastest computer I'm on. And then on this one, I took advantage. You can copy and paste the patterns of the codes. So, you know, you don't actually have to change. In this case, if you're adding to the depth of the circuit, it's just copy and paste, and you see how long the code is. And then I'm going to draw that. And then this is the biggest circuit, and this is the cover slide that I used here. So it's up to your imagination. Now, keep in mind, you want circuits that run, but it's really important just to experiment and find things out on your own. Now, on this next one, so this gives, so this little code here, this import KISS-kit, gives everything. So you see, previously they've been running 2 cores, 2 CPUs. Now this is 8, and then previously the RAM I saw was only like 6.7, which I'm assuming that'd be 8, because usually you wouldn't have 7 gigs. But anyways, it looks like they've been upgraded. So I'll show you later why. So here's another section of code, and then this basically will get the block sphere. So this code here, X. So this X gate, and then here, so 0 qubit. So it's kind of hard to tell on my screen, but you can see the errors basically. And it's somewhere in here. So I ran that, and then I ran this, then I ran that. And then we're going to run this. Huh. So I have to get back to that one. So basically, it's a block sphere, and it shows you in specific in that case. Now that's basically the end of that. Now I'm going to switch back to here. So view all jobs. Oh, it looks like it's done. So I think it hides it just because people do webcasts like this. It makes it frustrating because you have to look at the first couple letters instead of the ends of them. But basically it says that this completed. And so this is the first circuit. So remember this circuit that got built up. So this is a real quantum circuit that was used for Alzheimer's disease this year. And there's other papers that use the similar C0 pattern and rotational Y pattern. And this is what it is you'll have these distribution of probabilities here. And then remember, I labeled it by the author of the paper, how much deeper I went, and then how much wider. Okay, so that's one successful run. And then as far as analyzing it, what it means is this was used in conjunction with a classical network and a hybrid network. So it's similar to, and this is the first time I've run this circuit, just building it. So you can see, how the measurements were installed with that. And then the qubits, basically going down to 2+ qubits and 2+ layers. So that's good, so that ran as expected. And then the next step is basically, I'm going to switch over, and then we'll have time to talk about these in specifics. And I'm launching Python now. So Python has Anaconda, and we're done with Qiskit, basically. We got the results, and just need to further analyze it. And sometimes it gives a single probability, and sometimes it gives multiple. And I don't think it's noise, because you can check in the basically your circuit design what the exact or expected output is, and a lot of these are right on with that. So it just gives you that flexibility. So this is almost done, and then so I'm in Anaconda, and I'm launching Jupyter Lab. You have to be patient. If you keep clicking it, it doesn't like that. But it does bog things down, but it's still perfectly usable if I don't have other things open. So I've heard other people say that. Okay, so we're launched. And so we're going to do this. So this is basically another demo here. And we're going to share screen, and we're going to go here. So, okay. We should be share screen. Okay, so we're here. So I'm going to open up one of these, this trial 150. So I haven't ever run this before. And then, so in specific, we're going to go full screen too. So as you can see, this is a code. This is Penny Lane's code. And I'm going to zoom in just so everybody can see. Don't know what type of laptop you're on. So this specific one is using Penny Lane. Now, the Qiskit that I just ran, that's real hardware. And then on this specific one, it's a simulator. So the parameter I changed on this is this N train. So I changed it from 50 to 150. And it seems like it kind of maxed out about 80. So the default was 50 and my best accuracy. So I'll just show you kind of the code here. This is pulling from MNIST. So MNIST is a data set that's in Keras. And here's a bunch of the code. And then I'll show you, so this is a previous run, actually. Actually, this isn't the 150, this is a previous one. So what you do in this case is you go to edit, and then you go clear out all outputs. And then this one seems to be better than Qiskit as far as saving. meaning if you were just to exit out, would you still have your stuff? So as you can see, so this is a blank slate, and then this is the 150, which I haven't run before. And what you do is, it doesn't matter where you click really, and then you go to run, and then you go to run all cells. And then in the upper right-hand corner, it says the kernel status is busy, and you'll see that pi kind of counting down. Now, in previous runs, it's been anywhere from usually 3 to 4 minutes. This will probably be closer to 4 because of the end train. And what's kind of interesting in this, and it won't do it quite yet, is it'll start counting, and it'll say 1, 2, 3 for train, and it'll say 1, 2, 3 for test. Now, in this specific case, the test, so this is basically the fundamentals for machine learning, is 30. So it'll count to 150, and then I'll count to 30. And you can even run just sections of the code, and you can see in specific, oh, here we go. So quantum pre-processing of train images. So this is going to count up to that 150, okay? Then it's going to count up to, the 30. And so what I wanted to show is basically, we're going to have time for questions and comments, but kind of shoot through some things. And we're going to, let's see here. We'll come back to this. So keep in mind, the biggest things is it's going to show MNIST data set, and it's going to show accuracies. So we'll get back to this run, and then in specific, the results of that run. So, I don't close Anaconda and all that kind of stuff. Now, the other thing is a couple of slides. So here we go. So we have live demo, and then we're going to share this. So share to live demo. And then here, and this is the cover slide you've probably seen. Let's see here. Here's basically what's going to be covered. Is just for people not seeing this. And the case to make, basically for quantum and quantum sensing. Number one, for quantum sensing, better images, and then quantum computing, bigger data sets, larger kernel sizes. I'll show you one of these, basically these communications that talks about that. But there's just so much that's been done and that's being done, and then all these papers here. So left and right, quantum sensors, computers, anywhere from Fermilab, US president, it's their office, NIST. The list goes on and on with different aspects of quantum sensing and quantum hardware that can, definitely help this whole process of, better images and better data analysis of those new images. Now, Google, IBM, Quantinuum, and there's been a bunch of news, and we're still waiting for NSF's practical quantum computer. And also you have the hybrid 4-qubit simulators. They all seem to be 4 qubits. The ones I tested, I did 4, and I also went deeper, and I went wider with the circuit for the algorithms there too. And that's going to usher in these next generation of hybrid QNNs. I basically heard this podcast, University of Chicago, and they said single molecule detection, basically, at least, the quantum sensing, but, for processing as quantum computers get better, that's the thing. Now, I heard of this as far as, the mathematical advantages, especially, as you get to 100 qubits, you can't really do quantum simulators, say past, like functionally like 30, and I think theoretically past 50 because of the amount of RAM. But this paper said it's increasing kernel size becomes logarithmically slower, which is desired. So here it is, and here's the quantum circuit here, and then this is what's happening, with convolution as it would, and you can see the feedback loop kind of going between making a bigger kernel size, which we can't do too much of now, but that's basically what he called this is, bigger and cooler, QCNNs than CNNs. And this is fundamental to many aspects of quantum algorithms. So the 0 or the ON squared is, similar to, so these are convolutional neural nets. The amount of time it takes as you increase the kernel size. So the kernel size, and this came from the author of this YouTube video, he basically says it's basically, if you weren't to have your glasses on and everybody were to, have their hands on an elephant, they all would be reporting a different feature of that. And that kind of stuck with me. And the QCNNs basically, and especially as hardware emerges, getting better and better with that as well. So here's the circuit from 2022 for Alzheimer's. Again, this is used for hybrid neural nets, so not just the quantum. And then, so you'll see their 4-qubit circuit and the results. And this is similar to a different type of algorithm. Actually, the one I just ran, but just say don't make modifications to it. It looks like that. Adding a layer of depth, a single probability, adding 2 layers, a bunch of probabilities, adding 3 layers, a single probability. Now, 2 and 4 don't have that same, so the way you calculate that is 2 to the n number of qubits. So if this has 1, 2, they all have 4 because they're just deeper. So all of these lines will add up to 16. 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And you won't have any more lines than 16 is with that. So in specific, this is going wider in the circuit. So all of these showed all of the probabilities possible. So if you look at 7 qubits, which maxes out the IBM Nairobi, which I just ran on, you're looking at 128 probabilities for that specific one. So most people talk in terms of hundreds or thousands. So doing these tests gives you an appreciation for all the things in the minor minutiae or the minor other probabilities that you can get with, and this is just 7 qubits. So on this specific one, it's kind of summarized just what I said. Additional analysis has to be made on it. And then, in specific, they use this circuit, and you can see what I've been talking about as far as, width and depth and measurements and barriers, those types of things. So this is the Qiskit circuit that I just ran. So I translated this into, what was Qiskit, and then I added 2 more layers and then more width to the circuit. 2 other papers, this Kim Kamarayan this year, and then this Dong, this Y et al. As brain tumors. So 3 out of the 4 were Alzheimer's, and then this brain tumors one is 4 classifications instead of a binary. So harder task to do, more images. And then, so basically with this one, this is the previous slide translated into Qiskit. And then I had to put a barrier in there. They didn't quite show you, but if you don't, then these measurements kind of slide around. These results reflect to making the previous circuit or algorithm deeper. So every probability, single probability, every probability, single probability. And again, these all are 4 qubits. Look at the red H's. So those are all basically 1, 2, 3, 4, 1, 2. It's just deeper circuits. They're not wider. And this is basically, this bottom one is similar to what I just ran, except for this is the original depth, and it's just two qubits wider. So then you'll see 2 to the 4 probabilities, and then 6 qubits, so 2 to the 6, 64 bars possible. They don't always have to show. And this kind of shows, I talked about this. I had to insert code for the barrier and the measurements because they weren't working while dragging and dropping. Especially the barrier, it only does 1 or 2 qubits at a time, and then it didn't work. So you have to get a little familiar, with the code. Now the real quantum computing hardware. So this is fidelity over time. I ran this Grover's example. This is a search algorithm. It's very famous in quantum, and this is from February, and then this is in March, and it wasn't too much better. So the primary probability 985 to 991. And then this Bell state increased better. So this was my first circuit. You see really small, and you just basically click and it runs for you. November 27th, 506 and 432, the big peaks. And that's, your desired probability is 50-50. And then these little peaks, those are noise. And then this specific one, you could see 505, but then 466. So this one got better. Now, the one that really kind of threw me is I just reran this one to see where things at, because I ran it on March 1st. This is a modified, basically a Shor's algorithm or a piece to it. And you can see here, primary probability 682 out of 100, so 1024 shots. In quantum computing terms, you don't have, it's not deterministic, it's probabilistic. So you have to run a bunch of experiments, and then you take the average of, or you look at all the shots, and then you can take the average. So when I ran it in basically March 13th, a couple days ago, 838 compared to 682. And like I said, like all of a sudden I saw, like, instead of 2 CPUs, now it's 8. And instead of, 6 or 7 gigs of RAM, now it's 32. And then they're doing things, and you can see time in classical quantum computation. They're doing things on the classical side to make the quantum results better. So you have to research all this stuff basically to figure that out. So that's basically what the slide is the last one basically had the biggest improvement. Now, the one that's probably done running at this point is the penny lane, and it's similar to the other neuro imaging, radiology classification, either binary or binary or quaternary. So it's 4 qubits, quantum simulator, 4 layers. So 4 layers deep, and it doesn't show everything here, but it's poly Z gates, the RY gates. It's all these papers. There's so 4 of those, and then at least 2 COVID papers. They're all using just these really small quantum networks to help a bigger classical, say, convolutional neural network. Now, this is what's returned. This data set's relatively easy, so if you have, MNIST at the top, and then here you go. So as far as the results, you have, with more training, basically higher blue in those cases. And then also here, the loss is less. So this blue is lower, and it doesn't look like it overfitted, because typically overfitting is if you're if you have good training, but you have poor testing. So this testing loss was good. So that was good to see. Now, this has been run before, so it's predictable. Pretty predictable, between these 6 runs. They're, basically all the parameters, which is 80 training on this specific one. And then I tried out 77, 78, 79, 81, 82, and 83. And, not much better, not much worse for 77 through, say, 79. So that's kind of like that sweet spot, maybe 77 through 80. And then I checked a little bit below 77. Now, these are interesting because these are what pops up. So if you change the code a little bit, so this is what pops up for CIFAR 100, CIFAR 10, FMNIS. Sometimes the CIFAR 100, you can start to see it, human facial, kind of those kinds of details. FMNIS is the closest thing to the original MNIS. And then here's the results. So that FMNIS here, an accuracy higher than the CIFAR, didn't run very well, but it returned, the images, and then CIFAR 100. So the goal of all of this is to get brain, like Kaggle or ADNI or, all these brain data sets into either the, and this is a bunch of data that shows the 80 N-trains is the best. A bunch of these parameters didn't really matter. But the goal of this is to get all of this into quantum convolutional or convolutional neural net with brain data, and then start to get better classifications, for the startup. And then I got these downloaded. I was just having a hard time, getting the code right inside of Kaggle with that specific one. And then here's for reference. So this is the brain tumor, the quaternary classification accuracy. So I've referred to this paper a couple times. And then also with these, the accuracies, quantum versus author's conventional. So this is 5% boost if it has quantum, 7% boost, and then on this one, 4% boost. And then I'm going to switch back over to the penny lane to see the run, and then we'll open things up a little bit. So this one, share. So this one prints out just right inside the code. So you should be able to see this one. So yeah, okay. Here, so I'll try to stop where so we left off with this. So it successfully did 150 trains and 30 tests. And then here's the validation, or here's the input of the data. The top is the input, and the output's the next 3 rows, basically. See output. And then the next cool thing, so this is the part that has the quantum training. So you see Q underscore whatever. And these epochs, so epochs are like passes over it. So these 30 are the data that's going to go into the graphs I'm going to show you. Similarly, the C model, all of these epochs show up as the other color. So matplotlib is used to plot it. And then as you can see, the classical layer in this specific case was better than if you had the quantum layer. Now, it's interesting because the loss is not a reciprocal of accuracy, and the loss is about the same in this. And I knew 150 might have been a little big. So I showed you the Qiskit results. I showed you the penny lane. And then I'm kind of interesting as far as kind of where everybody's at with coding and maybe even just experimenting with the graphical interface. And we have some new people here. So Mary or Monica, do you have any questions or comments? And then if not, we have Tim or Ron. So I'm just curious as far as like the health aspect or coding, kind of where people are coming from. It's the kind of thing, yes, it takes a lot just to get into and to get a handle on, doing runs, but the most important thing is just running and then, learning off of videos or, those types of things, or reading tutorials, as you go along. So go ahead, Ron. Did you have something, Ron? So he said computer things. So, the key with all this is with healthcare. A lot of this is going to be going more into it. The things that has to pass right now, there's ISO IEC standards for cybersecurity for quantum, like quantum algorithms, run on classical computers for, defending against quantum attack from international countries. And once those pass, that'll set the tone for other things in life sciences and finance and, transportation, those types of things. And, there's a quantum software company. It's a spinoff of Google called Sandbox AQ. They just got $500 million. And this is basically to implement quantum algorithms into regular computers. You don't need a quantum computer to defend. So that set a tone, with that. And there's a law basically with, the US government. So actually, there's one thing I do have to think. It's not Ron's fault. Okay, so chat. Murphy's Law. So, all of that momentum is going to start to go into other areas just because, NSF says we have a practical quantum computer coming this year. And then, as far as we know, IonQ is still planning on a manufacturing facility. Go ahead, Ron.
Well, I just sent you an email, which you can ignore now.
Yeah,
Basically says you have everything disabled.
yeah, yeah. Did you have some, Ron?
Yeah, the the IBM experience. Have you noticed if they have support where you can go back and forth between the text lab and the circuit lab? Or like, for example, you write some code over in the Qiskit Jupyter notebook, render it to Quasm, and then take that over and have it assemble the circuit in the other
Yeah, as far as
in the other one.
as far as I know, you can. I know for sure you can have multiple windows. So, for instance, I'd have all jobs open, and then I'd be designing. That's where they should like the results, and then I'd be designing a quantum circuit and composer. So yes, as far as I know, just that's the thing. It's meant for people to get hooked on quantum. Like I said, the smaller, unless you give them a credit card, they can't really charge you. But that's what other people say. It's a free service, unless you want to use their bigger quantum computers. And it's at this point just experimenting, so it's different levels of experimentation. But yeah, with OpenQASM, it's very, very shorthand. The code is very short, so it's just easy. I think it's, if you want Hadamard, it's just H dot, maybe a couple, like a parenthesis, and then bracket qubit, and then close bracket parenthesis. It's really short. The one thing you can't do is you can't edit OpenQASM, or how is this?
Sure. Yeah. So the reason I'm asking is because I noticed the one circuit that you were in the IBM circuit lab you were showing is just basically a big massive repetition. So I'm wondering if in the graphical side, whether they have the ability to like build an oracle or just build a circuit fragment which you can just replicate. I know you can do it in Qiskit. I've done some techniques there where you just basically write a function like you do in any language, and then you pass it the qubit state, and basically you can call a function that just says add these gates, and then you can just keep calling that function as many times as you want to replicate the gate sequence. So that would be good if you could write code over there in the Qiskit side, and then just once it generates QASM, that you can just take it back to the circuit side and see what it looks like over there, or be able to manipulate it over there too.
Yeah, and I just encourage everybody is just to get out and test these things. The only way you find out is, I mean, for everything that works well, maybe 9 or 10 things don't. It's that type of thing. Like I said, like barriers and measurements. And I basically did a set of these, and it was just like I had to redo a bunch of them because my measurements weren't right. And that's what it took. It took a lot of experiment. So you can edit in OpenQASM for sure. And then what you're talking about is sounding like it's getting into, in specific, other services, besides Qiskit, I would say is more just kind of straightforward. So
no, I mean, I'm a compiler tool chain person, so one of my favorite things to do is write code that writes code. Okay, so in the Jupyter notebook, I can easily write a function that builds a circuit fragment, and if I call it twice, if I just call the thing twice, it'll just replicate that circuit down the chain. I notice on one of your circuits, there's like I don't know, you had like 4 qubits or 6 qubits, and there was like 7 or 8 gates that were just repeated a dozen times, and you're doing that manually, dragging gates onto the circuit. I'm just saying, is if you can encapsulate that little chunk of gates into an oracle or into or into a subroutine, then you could just,
Yeah.
just call a function to add another one, add another one, add another one.
What I was doing before, when I was just like super focused only on the code, is I could copy and paste that specific chunk if I was going
Okay.
in the circuit, and that was super easy without having to do anything else. Now, if you go more qubits, I don't think you can do that quite as easy here, to go wider in your circuits. But
yeah, I was just actually, because I haven't played that much with the circuit lab, but I've done more work in the like in the Jupyter Notebook Qiskit side, and you have I think you have more power there, but you have more simplicity in the circuit lab, and it's easier to visualize what's going on quicker, and you don't have to explicitly tell the code to draw your circuit. It's right there.
Yeah, and I don't think it would be just me that would tell you it's limited. Even to say the number of gates that I went over from single to double to triple gates, I don't think they're all listed in that block. So yeah, I mean, I think what probably people are doing is, you do the open chasm and then you put it into graphical to take a look at it. And there's other graphical viewers on the web too. So just, just apart from Qiskit. Now, I know there's differences between QML and Penny Lane and then IBM's Qiskit, as far as code. And I've tried to copy and paste Penny Lane code into Qiskits, and it'll import. But I think the issue is, the gates and everything aren't the same as Qiskits. So it's trying to be the standard. Or I know that IBM's opening it up, besides just gate-based superconducting qubits, they're opening things up to other hardware modalities. Just say if it's going to take a little bit longer with their technology that they focus on. So it'll be interesting. You probably know better than I would as far as how technology pans out, and VHS tapes and Betamax. It's just usually.
Yeah, I get the feeling that Penny Lane is just like, we're not going to worry about hardware. We're going to build our framework such that we can invent any unitary gate that's legal and use it. And there's an infinite number of unitary gates, but they're not all implemented. You can't implement all of them on actual hardware. But if you're only going to be running our big 30-bit simulator, we don't care. We'll just let you run it. So
yeah, we'll go to Tim. Go ahead, Tim.
Yes, for that large circuit that you showed at the beginning of your talk, what is the purpose of all those RY gates?
Well, the original circuit is 6 layers of that repeating code. So, and there's like, say like, there's 4 brain papers that use that similar type of thing. So 6 layers, 4 qubits. So, I mean, just the fundamental level is its rotations, right? So if you have a qubit and then it's turning, so an RY gate, first you look at a Y gate, what that does, and an RY gate rotates that. So there's, decent, you don't want to get stuck only doing these, but, block sphere and say, so when you go across, when you go deeper, so from left to right, you're looking at a single qubit. Now, at that same time, that single qubit, if it has 4 or if it has 3 or 5 other qubits, it's synced up with that other qubit. Say if it's a C0 gate. So if you have, in many circuits, it'll be, you set initialization, Hadamard, and then that sets the superpositioning of that single qubit, and then you're doing entanglement through a C0 gate. So it's, and I've heard of this before, is like the time, between, say, this qubit and then that qubit, they're supposed to be in sync, but I don't think that's always the case. But, one qubit could be doing something at a certain time at RY gate, and then the next qubit, so say qubit 0 to qubit 1, 2 qubits, is doing something different at that time. So that's how it's been explained to me, is it's a time, left to right. So that specific thing is happening to that qubit. Something's totally different, in a different rotation, an eighth turn, quarter turn, half turn, those types of things can be happening. And that's what gives the circuits the functionality.
Yeah, and that gets back to what I was talking about, having the ability to isolate those separate blocks into a single function. Because what's going on there, and Kevin, you talked about Grover's algorithm. Once the initial calculation is done, what needs to happen is you get a quantum state based on your quantum bits, which form a quantum register. And what you need to do is, now it's like you've got a list of probabilities, right? So what you need to do is, the next step you need to do is run what they call an amplification pass. The amplification might be that, that little block of code of gates. It runs an amplification algorithm, which basically flips the phases and around what they call flipping the phase around the median, the median value. And so what that has a tendency to do is to amplify the higher probabilities and lower the lower probabilities. But if you only do it once, you may not have adjusted your probabilities to be in a comfortable zone. So do the exact same set of gates one more time. Now you've done an amplification on top of an amplification, and every time you do an amplification, it drives the correct values towards 1 and the incorrect values towards 0. It's almost akin to, in classical image processing, a type of contrast flip. But that's why, like Kevin was showing, that every time he adds more of those gate blocks, he gets better results, because and I'm guessing here, but I'm pretty sure that's what's happening. Every time you add a block, you're adding another amplification circuit, which again has the ability in quantum to pull out the good answers and suppress the bad answers.
Yeah, I'm posting in the chat. So where I started, well, the second thing that I did was basically I went through all the gates of the Qiskit gates, and you could do it in frame. I don't even know if you need to have an IBM account. So if you click on that link, and sometimes it's easier just to take out all their markdown. So markdown is text that's not related, that's not hashtag, that's part of code. And then just have, just keep running and say, oh, okay, I just noticed this part of the circuit, and that's what makes, the output look like that. And that's a win. But it's hard for a lot of the tutorials to do everything, both read and theoretically understand. That's what I find myself doing, is I'll go back and forth, I'll read the theoretical, and then I'll run, then I'll go back, and then I'll, see what I noticed when I read is happening to say in this case, the gates. So I would do that. Like I said, I don't think you need an IBM account, because it's just running inside their own thing. You do have to run, setting up their whatever simulator, that kind of stuff. You control enter, control enter, control enter.
Yeah, but you can sign up for free, and you really want to do that if you're going to play with it, so that you can save your own work. Otherwise, if you go mess with the documentation simulators, so you can play with them, but then when you leave, everything you've done is gone. So
yeah,
just sign up, because it'll keep the work that the work that you've done in your account.
Yeah, it's I mean, there's services out there like Classic or sorry, oh, I can never remember this name. Classic just had a
Quantique.
No, not Quantique. It's they just Australian based Q Control. So Q Control basically has a bunch of software tricks that will help you get better results when you're running on quantum computers. So and I think they can back it up and say, yes, we can do that, and your data is valid if you pay whatever. But one of the things I glossed over is it's actually good to run on these lower qubit quantum hardware, like the real quantum computers, because it amplifies what's wrong with your circuit. So as bigger, not necessarily even bigger, but like less error prone. So you want to start off small. So if you're building up a circuit, to design something, it's good to run that chunk of code on a smaller quantum computer, A, because it's free, and then B, because it's going to highlight certain, especially if it's older quantum computer, it's going to highlight the errors and the probabilities you'll get that you wouldn't get on a better quantum computer. Do you see what I mean? Like it exposes like the errors and flaws. So, those 3 circuits that I ran, one was back in November. One, like Ron said, was the Grover's, and then another one was kind of like a modified Shores, or, part of a Shores. And, and especially for the more complex circuits, they seem to be getting better over time because the quantum computers are getting better over time. Now, we could talk about this all day, but basically there's code that is inserted into quantum simulators to make them run noisy like a quantum computer would. So it's a relatively exciting field. It's not nearly the size and scale of classical, but it's still something that like a hockey player taking a slap shot, if this practical quantum computer we get this year is good, significantly better. So we'll see. Okay, so is there anybody else? Should be able to unmute, or I can unmute. Okay. And then anybody we haven't heard from? Go ahead, Ron.
I was just saying that we have to figure out a way to be able to send you Morse code with the with the hand raising or something.
Oh yeah. And then so
can tell you to turn things on.
Yeah. So John's coming back on here too. But yeah, I guess if anybody has any questions or comments, I'm kind of interested, where people are coming from. I know where some of the people are coming from in the chat right now, but I personally see that once the cybersecurity, because it's a law, it's a law that you have to for federal agencies under the U.S. government to start implementing quantum cybersecurity that passed in December. So for me, a lot of people just react, they say, oh, okay, well, it's, all these other industries don't have that yet, but you see it's going in that direction, and there's been billions of dollars, and, the U.S. government spent $800 million each year the past couple of years, kind of thing. So I just put all these things together. I'm like, wouldn't you want to figure out an application for quantum, that you want to go into or currently are in? So, but it just takes time. The Sandbox AQ is a huge thing for, like, compared to the other startups, it's $500 million. And I don't think it's gotten all of it, up front yet, but, even Rigetti has gotten $100 million. And, there's other startups that are in that range, I don't know how many digits, $100 million plus. So awesome. So is there anybody else we haven't heard from? And then if not,
I joined late, so
yeah, go ahead, John.
Sorry about that. I was really, for some reason, I put these links in there, they don't seem to come up, so that's an issue. But I have to keep more attentive to these Thursday meetings. My question is, joining late, is you had a link there you said something about, and since it didn't pop up when it populated. when you were talking about blocks, you actually were referring to blockchaining with the quantum. Each gate essentially becomes a block of code unto itself.
I mean, not specifically. That's been mentioned, with quantum. I didn't cover that. So I've been covering, deepness of a network, or, wideness. So then the first thing I did is basically adding specific gates and then running it, getting the results.
Sure.
So,
yeah, I used to do electronics back in the classical electronics. So essentially gates were important, for outcome, because you were trying to get, at the time, basically software. When I started, basically software wasn't there. It was more gates rather than ASICs. As you've seen, as you heard ASICs before.
I'm not too familiar, but yeah.
Well, it's basically a coded, it's a coded gate. Essentially what you're doing with these gates is kind of like an ASIC idea. You put this inside a chip, and that chip then gets burned, and it's either permanent or it's not permanent, but that gate basically is there. So everything works. So you have to go out and get a whole bunch of gates on a board, and you just add things to it as you go along. So that's what I was trying to get a better picture real quick. When you're starting out, because you understood what you were looking for as a result. What did you understand that? Or you just looked at the result and just looked for the error correction on it?
I mean, it's more making modifications to algorithms that people already use in industry. And then, if they had, 4 qubits to 6 qubits, or if it has 6 layers to 8 layers, those types of things. So I think, and even Ron might be able to tell you a little bit better as far as like the quantum gates are software based. So they're actually terms, so if you have a turn that's half, so it just goes like that. There's certain gates that do half turns, certain gates that do quarter, and you'll have neither qubits over there, but these are lacrosse balls. So you'll have, 2 qubits that go, and the time should line up, but this one might be turning this way, and then the other one might be turning the other way as they go through the same time sequence. Now, the kind of the buzz these days is a thing called dynamic circuits. So if a quantum, if your bit is not good at a specific operation at a specific time, and it's better to do it classically, you'll have the classical computer that sits close to the quantum computer, and within that time period of coherence, decoherence, these types of things, is an operation is completed better with classical than it is with quantum, just because of the development level of classical's better than quantum. And a classical computer still can't perform quantum mechanics. I mean, it can simulate it, but when you're talking about real-time speed and a real quantum computer, I think with dynamic circuits, you're not going to see that as far as a classical computer, simulating quantum mechanics. It's basically substituting a task that a quantum computer is having a hard time with. Now, what I've heard from other people too is that as you go across, every single operation picks up some little error. And, if you have, and this is going to be the case moving forward, I heard one person once say, simulators are better to go deeper. And then quantum computers are better to go wider with more qubits, because of that chain of, neural networkness of deep layers, that kind of stuff. But the issue, obviously, we all know is as we go higher in qubits that we're more susceptible to error. So there's a lot of things that are kind of like, okay, well, we would like, it should work this way, but then we have this other issue here. So, I mean, still in reading literature in these hybrid neural nets, for tumors and Alzheimer's, and even before that, there was COVID, especially with COVID, is that they're always kind of using some bigger convolutional neural net just for imaging. And then, like the smaller quantum circuit for a specific task, simulated. So it'll be interesting. So, if we were to predict which technology might be closest to a fully connected neural network. Well, as far as I know, ion trap is the only one that can do that, because the quantum computers, due to their circuit connectivity, they can't do that. But that's the hope, right? The 2023 practical computer by NSF, MIT, basically in their reviews, they said that this is the year that we're going to stop worrying about hardware and error and be more concerned about researchers consolidating, their works in quantum, to actually, this is the year to start doing some awesome stuff. And keep in mind,
that's a good news. I mean, because the idea is that I found the hardware, at least when I get back into this stuff, I'm really trying to, I need to fundamentally get more money coming in. So the idea has been highly distracting. This, I should be down the road on this stuff. But yeah, I totally agree with the fact the hardware is there. And it's just a question of basically developing everything you want to develop and then looking for the errors and try to figure out, like they did with automated cars. They start testing with small things and then you kill some people. But the idea, that was oops kind of situation. But you want to avoid that, especially before because it's all going to go FDA once you. So it was going to be in the laboratory for the longest time before the FDA looks at approval for these models. So you can play around and give them time to play with everything else. And I'm just looking at how to get into coding enough to basically creatively look at things and basically be able to process. And I'm looking at, when I took a class with, I forgot the gentleman's name, there were a couple of guys, a couple summers ago, basically my concern was error, because if you look at the block sphere, and the block sphere itself basically shows within 3 axes, you don't know where this thing's supposed to be. But if you're knowing that you're going to try to focus on forcing these things to this position, then essentially you're saying you're coming into one of the other angles that basically, so you got 3 things going on at one time. So one position, like a clock. Again, we're back to, remember, like computers are clocks anyway. So each one gets a move. And if you can get that down to that mechanical process, then essentially you can predict how that gear is going to work. Because in just using clocks as an analogy, the clock design basically went through such a transition where the gears were made so proficient that they meshed and didn't lock up, And just using that was my interest as we kind of focus this, because every time you have a clock movement in a classical computer, there's one bit of electron moves across there, So as they got faster and faster, you can actually process more electrons. Because down on that level, everything's down at lithography level, and they see you have these holes and everything pops in there and pops in there and pops in there and moves on. And then basically any heat that transfers out, basically heat transfers out that hits the lattice structure. And then, I used to like blow things up. So you want to test how these things worked and see exactly, get an idea how the electronics, how they actually developed mil-spec, that industrial military thing that went away, or how you had commercial grade. So I'm just kind of not going to classical, but understanding classical and quantum as relatively the same, but different. Okay. Does that make sense?
Yeah, I mean, what came to mind is I read some of these, they're like financial outlooks. It's the INQ, and what they did is they'll put like a small block of representing, air. And it might be like 50 or 100 dots. And then it has, like, they say all of their other competitors, and it has like thousands of dots kind of like encroaching in on it. And it'll be interesting because, we all know that, qubit counts, IBM keeps going higher. I think even by 2026, 2028, INQ is saying only 1,000 qubits. But for, imaging and radiology and those types of things, if they're really good, then, we're talking, you can have pretty good quantum advantage, even 100, 100 qubits, depending on your task. Now to simulate, molecules like a caffeine molecule and all that kind of stuff, and, other proteins and receptors, you're talking millions of qubits. So, that's the thing with drug discoveries, they're they're approximating things as they should with D-wave annealing. So, and it may have a cultural impact this year because there's a Nature paper that came out last Thursday. If you don't know what happened, on Friday, you can read. But basically, it's saying that using quantum annealing, that it can help prevent any type of, it can help prevent certain types of bank whatevers. So if quantum saves the day, that's basically the thing. And it's not going to hurt the other applications, that people are going after, such as the startup and other types of fields too.
No,
But
I really agree. What was the name of the paper? Do you know?
so it's Nature. Let's see. I could tell you the date. Nature. I think it was okay. So March 8th or 9th. I want to say it was the 9th.
No,
then, wait. Yeah, they used quantum annealing, optimizations and these types of things. But it was interesting because it came out middle to late week last week. So
no, I think especially when you're trying. My thing is when you're looking at how these things. Well, drugs are one thing where you test eventually. You have an understanding. And the reason drugs look like they do, and the lawyers look at the law and all those ads, is because a lot of drugs go everywhere. So specifically, while you design it for a receptor someplace, there's a chance that it's possibly going to go someplace else, and you want to know what that drug is going to do, right? I mean, that's my understanding of the hit or miss thing of pharmaceuticals, and then you test that to the point where you can. What's that?
Ron, what is that?
What's Ron got? Looks like a board.
This is a circuit some company is mass producing. It goes inside of like what looks like a wristwatch. They hand out 80, 100,000 of these at football games or whatever. The two white squares are RGB LEDs. Okay.
It's not in focus, that's why.
Yeah, I don't have a good camera. The black thing right under my finger is a IR receiver, infrared receiver.
Is that like a what's that? NASCAR. NASCAR has this program where you walk into NASCAR world and they just want everything and everybody to understand NASCAR.
So like no, this is like, so it's like you go to a football game and they give you this little thing, looks like a watch. It's got one of these in it, and it's got these two RGB LEDs and the IR receiver. And what happens is when they get to halftime, they have everybody hold their hand up.
Oh, I got you.
And something in the stadium talks to this thing, and the whole stadium lights up.
Oh, I got you.
And they start drawing patterns around the around the audience. So, but the thing that you were talking about before is this little sucker, and I'm sorry it doesn't want to focus, but there is a serial EEPROM on here, and this other chip right there is a field programmable gate array.
Right.
And so I've got a handful of these, and I'm thinking, I've been looking into doing, but I don't have. The manufacturer of this thing does not want us to know what these parts are. So I have to try to figure out what the parts are. They actually scraped all of the numbers off. But I want to turn one of these into a qubit.
Okay.
And then see how many of them I can connect together.
How do you, I like the idea what they're doing, because I went to a NASCAR talk one time. NASCAR has this thing where similar, but they want you to walk in the NASCAR world and enjoy the entire experience of NASCAR. And it's all about NASCAR. And it's like that kind of thing. My thing was with the gates, that's what we were talking about before. I lost my train of thought.
Yeah, and you're talking about classical gates, and unfortunately, there's a lot of unfortunate words in the quantum dictionary, and gates is one of them. And they have nothing to do with classical gates.
Oh no, I understand that, but the idea is you're still getting some kind of output, some kind of input.
Yeah.
So you're still
Yeah, actually,
huh?
actually, a quantum gate has to be told to do it, whereas a classical gate just does it. It doesn't. It'll sit there forever and do the same thing over and over, or
Exactly.
or statically. But the thing that made me think about this little circuit board was you were talking about ASICs, and when I realized what you're talking about are field programmable gate arrays. These things are logic circuits that could be programmed on the fly, and that's more akin to what a qubit is. You basically just keep modifying the qubit on the fly. So I have to see what sort of interesting things I can get this little sucker to do someday.
Well, it seems like as they refine this, they're talking about a field of qubits that basically all start changing states. And as they change states, that's a result. And that result basically then adds to the final program. And that's where, and in other words, what you normally would take in a classical computer, basically all that circuitry essentially becomes these qubits, which have been your circuitry, because you're actually forming them to what you want to do. That's my understanding of how this stuff is kind of progressing. But that's open to open interpretation study, you know. And like especially with drugs, especially with the application. Now the neural net stuff, I'm still puzzled how they're how would you have to have a solid neural net, you know, if you understand a neural net. And each nerve basically is part of something that connects to something based upon how this ganglion connection and these gaps are, you know, aligned with each other.
That's another one of those artificial neural nets are not really a whole lot like biological neural nets.
Right.
They have symmetry. They have known connectivity. They have all kinds of things, and a lot of that has to do with us being able to manipulate them using matrices, you know, so we understand the math and we can make them useful. It's very hard to mathematically model an actual neuron because you don't know how you don't know things like the size, the number of connections. You don't know what the weights are. You don't really have there's only certain ways to change the connections, change the weights.
Well, so my understanding of a nerve, basically, you know, it's electrical connection goes down the length of it and then goes into a chemical process, gets encapsulated and gets shot across the synapse, and there's a receptor on the other side that picks it up and translates it back to an electrical signal again. So
right.
And that's
but what I'm saying though is the neural nets that are used in machine learning are very symmetric. They're very orthogonal. They're very well structured, and the different layers tend to be, you know, somewhat identical. Whereas in a human brain, there's the augmentation of the net is all evolves over the lifetime of the individual. So it's not, you know, they call them neural nets, but again, another unfortunate choice of words.
Well, yeah, it is. I mean, I study animals, and I've been studying like grackles and crows and geese and ducks for the last 6 or 7 years, and they're like going on 12 years on the grackles. And basically, I did a stint. Basically, I decided to drive a special needs vehicle, and I was just kind of I hate to say it this way, but I was studying the kids I was taking in because some of them have Down syndrome. One was a survivor of a shaken baby syndrome. Somebody really broke this person, and just understanding how the connection, the person was trapped inside this broken body with no real way to communicate out other than a sound, and basically that was it. So with those connections broken to those, you know, the auditory system, the optical system, to the speech centers, that person, you know, they're intelligent, maybe, but you don't know how much damage was actually done, how much was healing. Because if you remember, like 10,000 years ago, some genius doctor goes, you know, the brain doesn't repair itself. And I'm going, how stupid can you be? You know, I'm an evolutionist by interest. all the other stuff in the fascinating world of everything. Just you can debate how that works, but it's kind of a model that helps put these things together and how they repair themselves when they get damaged. So if you're going to map them out, your brain, I was just listening to NPR today talking about how this gentleman up, I think he's up at Hopkins, he was studying how we listen and interpret music and where all the pieces of music goes to, left and stored in the speech center, the language center. But then again, other parts of the music get it to other parts of the brain. So it's this synapse basically splits all of these pieces and then basically comes back together and you get the toe tapping thing. Okay, so yeah, that's my curiosity with all this stuff, how it actually works and how it functions through the magic of separation, where the brain actually makes the decision points that basically send it off to these location centers in order to retrieve that information later. Basically, I'm a musical person. I did vocals for a long time, so I listen to the world differently than most people. And I used to have a higher range than I have now. That's why my voice sounds like it does, because I used to push the envelope up there so it becomes nasally. Okay, another way, when I get on a microphone, it's a whole different story. I talk like this, but when I'm talking normally, it's relaxed. So it's kind of like how I think of the world and see the world is different from people who listen to music, as opposed to you have to hear it, and I can mimic it very easily, different sounds, animal sounds. So that's kind of where this stuff has a fascination for me, to be able to duplicate, what Kevin, and I'm sorry I missed the first part of the Zoom, because I really wanted to figure out some of the information, but
Yeah, and
that's kind of where I
am. As far as quantum goes, like, where it excels, like number of parameters, time. Like I shared an example today, and it's basically saying quantum could get a lot bigger in kernel size, which is for imaging or convolutional neural nets, where, classical, it's basically n squared for classical, but log n. So log n is similar to the Shor's algorithm too. But that's where it's gonna, it's always like, oh, if I only had a quantum computer that was a certain number of qubits and didn't have as much error, then I could do this task, because it's not just because quantum computers are always better, those types of things. So very interesting. Well, I appreciate everybody. This has been discussion 74, March 16th, 2023. This will be up on YouTube. Have a good rest of the day and have a productive rest of the week. Take care.
All right, thanks, Kevin.
Thanks.